Hello students, here is a problem on indeterminate frames solved and analyzed by the method of least torque, and also we are required to draw shear and moment diagrams and the sketching of the elastic curve. So by method of least torque, we have this frame is indeterminate to the third degree. So I choose AH, AV, and MA as the redundant forces. So we have two section portion of the frame. This is the first section, second section, and third section. Since the slope of the sloping member AB is 5 horizontal, 12 meters vertical, therefore if the length is x, this is 12 over 13x, and this is 5 over 13x. The length of AB is 13 meters also. Then for this other sloping end, the slope is 12 vertical to 3 horizontal. 12 divided by 3 is 4, so we can reduce it to 4 vertical, 1 horizontal. So the hypotenuse is square root of 17. Therefore, if this is x, this is x over square root of 17, and this is 4x over square root of 17. So first, partial of work with respect to the first redundant AH. So these are the assumed directions so that whenever they are involved in the moment equation, they are always positive. So the moment at this section is EH times 12 over 13x plus AV times 5 over 13x plus MA. Then the derivative of this moment equation with respect to the first redundant EH is 12 over 13x dx. Then we divide the entire integrand with 2 because the moment of inertia is 2i. So divide by 2. For the next section here, the moment equation is EH times 12 EH times 12 or 12 EH plus AV times 5 plus X, AV quantity 5 plus X plus MA, then minus the moment of this loading 20 times X over 2 or 10X squared. So minus 10X squared, the derivative of this moment equation with respect to AH is 12, so 12 dx. And finally, in this section here, the moment here is EH times 12 meters minus 4x over 17. EH quantity 12 minus 4x over 17 plus AV times 5 plus 8, 13 plus x over 17. So 13 plus x over square root of 17 plus MA. Then plus the moment of the 15 kilonewton load, 15 times 4x over square root of 17, and minus the moment of this loading, 20 times 8 times moment arm 4 plus x over square root of 17. Then the derivative of this moment equation with respect to AH is 12 minus 4x over square root of 17 dx, and the entire integral is divided by 1.5 because the moment of inertia of CD is 1.5. So evaluating first coefficient of AH, integral of 12 over 13x times 12 over 13x divided by 2, 0 to 13, that would be 312 AH. Then integral of quantity 5 over 13x times 12 over 13x dx over 2, that would be 130 times AV. Then integral of 12 over 13x dx over 2, 0 to 13, 39 MA. Then for this next integral for AH, 1152 AH, for AV, 864 AV, for MA, 96 MA, and for the constant negative 20,480. For For the next integral, for AH, integral of quantity 12 minus 4x over square root of 17 times 12 minus 4x over square root of 17 dx, or simply integral of quantity 12 minus 4x over 7 square root of 17 squared, 0 to 3 square root of 17. By the way, the length of this member CD is square root of 3 squared plus 12 squared. That would be 3 square root of 17. That's why the limits is 3 square root of 17. The entire integral divided by 1.5. Moment of inertia is 1.5. So the value is 395.818 EH for AV 692.682, then 49.477 MA, and for the constant, negative 36,613.178. Combining like terms, then we'll have our first equation, 1859.818 plus 1686.682 AV, 1859.818 AH plus 1686.682 AV plus 184.477 MA equals 57,093.178. Call that equation 1. Next, partial derivative of u with respect to AV equals 0. We copy the moment equation, we just change the derivative. So the derivative of this moment equation with respect to AV is 5 over 13x dx, and divided by 2. For the next integral, copy the derivative is 5 plus x dx, 0 to 8. Then for the last, copy the moment equation. We just replace this by the derivative of AV, which is 13 plus x over square root of 17 and divided by 1.5. So integrating, so the first integral from 0 to 13, the length of AB is 13 meters. So we have 130 AH plus 325 over 6 AV plus 16.25 MA. For the next integral, we have 864 EH plus 2072 over 3 AV plus 72 MA, and for the constant, negative 56,320 over 3. And for the last integral, we have 692.682 AH, 1,739.951 AV, plus 119.570 MA. Then for the constant, negative 95,078.816. All divided by 1.5. Take note, these are the results. So combining like terms, we have 1686.682 AH plus 2484.784 AV plus 207.82 MA equals 113,852.149. That's equation 2. And finally, partial of u with respect to the third redundant MA equals 0. So copy the moment, divide by 2. Derivative of MA is 1 dx, or simply dx. Copy the second integral, derivative of with respect to MA is dx. Copy the third integral moment equation, the derivative with respect to MA is just dx. So the value of the integral would be 39 EH plus 16.25 AV plus 6.5 MA plus 96 here, 96 EH plus 72 AV plus 8 MA minus 5,020 over 3, then plus 49.477 EH plus 119.570 AV plus 2 square root of 17 MA minus 6,514.507. Combining like terms, so we have 184.477 EH plus 207.82 AV plus 22.746 MA equals 8,221.174. So solving equations 1, 2, and 3 simultaneously, we get AH negative 26.57 kilonewtons, AV 66.159 kilonewtons, MA negative 27.536 kilonewtons. So the negative sign indicates that the assumed direction is wrong. It would be the opposite direction. So AH should be rightward and moment A should be counterclockwise here. So we're now ready to sketch the shear and moment diagram, but before that, let's solve for the shear forces. Transmit the reactions. This is the table for the answers at reactions at node 1, which is A, and node 4, which is D, by the software RISA. And if you check, that's correct. AH is rightward, 26.57, 66.159, it checks. 27.538, it's just 27.535. So there is a very, very, very negligible discrepancy in moment, but practically they are equal. So for the reactions, these are the transmitted reactions and the actual direction of moment. So at this joint here, the positive shear, this is the top fiber here, this side. So positive shear would be in that direction. Let's now compute the shear in AB. So this is the positive direction for shear. This is the slope theta 1. So this is also theta 1. Therefore, the component of 66.159 should be positive in that direction, and that is adjacent to theta 1. So that's why 26.57, which is rightward, the shear component is in the opposite direction, so it is rated negative, and it is opposite of theta 1. So therefore, shear in AB is 66.159, this component here in that direction, opposite or adjacent to this angle theta 1, that's theta 1. This is also theta 1. So 66.159 times cosine of theta 1, and cosine of theta 1 is 5 over 13. 5 over hypotenuse 13. Then minus 26.57 sine of theta 1, which is 12 over 13. So it is 0.9196 kilonewton. Notice that for member 1, the shear is 0.919. So it checks only in this last part where there is very negligible discrepancy. They are practically the same. Then, considering the entire system, summation forces horizontal, so we have 26.57 rightward plus 15, then minus DH, which is assumed leftward, equals 0. So DH is really 41.57 leftward. 41.57 node 4. Negative means leftward. Then summation moment D, assuming this is the direction for moment at D, which is counterclockwise. So summation moment D equals 0. MD plus the moment of the 20 kilonewton load, 20 times 8, 4 plus 3 is 7. Then plus 27.538, which is moment at A. Then equals 15 times 12, moment at D, plus 66.159 times 16. 5 plus 8 plus 3 is 16. So moment at D is 91.006 kilonewton meter. In the software, it is 91.005. So that's fine. They are practically the same. Then considering AB, assuming this is the direction of MBA, summation of moment about B equals 0. So MBA plus 66.159 times 5, then equals 26.57 times 12 plus 27.538. So MBA is 15.583, and that is correct in that direction. Then considering BC, this is the direction of NCB clockwise as assumed here. And let's transmit MBA, which is now counterclockwise, and it is 15.503. So MCB, summation moment C equals 0. Considering this BC here, MCB plus 66.159 times 8, then equals this moment, which is MBA, which is MBC, counterclockwise 15.583, plus the moment of the load 20 times 8 times 4, and we get MCB to be 126.311 kilonewton meter. So member force 126.315 only here for MCB for member 2. So that's fine. And finally, for shear in DH, this is the positive direction for shear. This is the top fiber, positive in that direction. Since there's no other load on this member, whatever is the result here for shear, it is equal to the shear at C, but opposite in direction. So computing the shear in D, shear in DC, which is, I assume, positive in that direction. So the component of DV, which is 93.841 by summing up forces vertical 93.841, is in that direction, so it is positive, and the slope is 1 horizontal, 4 vertical, square root of 17 hypotenuse. So this is 93.841 times 1 over square root of 17. 93.841 times 1 over square root of 17. The component of DH is in the negative direction, which is here, longer. So minus DH 41.57 times 4 over square root of 17. So the shear in DC is negative 17.569, so it means it is in this direction, so that the shear at C is positive in the up to the right direction. So they are equal, but 17.569. If you check for member CD, member 3, the shear is indeed 17.569 kilonewtons. So that checks. We are now ready to sketch the shear diagram. First is shear in AB is positive 0.9196. So positive in that direction, 0.9196. So that remains constant. And since there's no other load at B, it should close. Then this is vertical component at A, reaction. That's also vertical component of reaction here because there's no other load for member AB. So 66.159, then minus 20 times 8, times 20 times 8, negative 93.841 for member 2. So that's why you have here shear negative 93.841. Then it should close because the reaction at D, vertical reaction at D is 93.841. Then we have 17.569 because this is negative here, so it's positive at the other end C. 17.569 constant, then minus 17.569, so that's why it closes here. So this is the shear diagram. This distance, which is 3.30795 meters, is obtained as 66.159, that's the shortcut, divided by 20, so 3.30795 meters. Or the other way is, if you're not familiar with my technique, that is actually shear equation equate to 0. So the shortcut is shear divided by the uniform load 20. So 3.30795 meters. And this distance is 8 meters minus 3.30795, 4.69205 meters. Then the rest, we can compute the area. 109.425, 1 half of 3.30795 times 66.159, 1 half of 4.69205 times 93.841, so negative 220.153. This area is simply 17.569 times the length of this member, 3 square root of 17 is 217.317 kilonewtons. So beginning with the moment here, which is negative because the positive direction is there, so negative 27.538, then plus the area 0.9196 times 13, so it is negative 15.583 here, so it should close the shear. Then the moment rather, negative 15.583, negative 15.585 in the software, so that's fine. Negative 15.583 plus 109.425 positive decreasing is 93.842. 93.842 plus negative 220.153, negative increasing, negative 126.311. And for the last number, beginning with negative 126.311 plus the area, which is 217.317, so that's why you have 91.006 for the last number, 91.006 kilonewton meter. So this is the moment diagram, and therefore for the elastic curve, we have point of inflection here, point of inflection here, and here. 3 points of inflection. This is negative moment, so it is concave down. This is the upper fiber. So concave down, you look at in that direction. Imagine that's horizontal. So concave down, then we have concave down for this portion, concave up for this portion, concave down, concave up. Then negative moment means concave down again. Then negative moment in this portion here is concave down. We have point of inflection, which is this. Since this is positive moment, so it is concave up. You view the last member in that direction as positive because this is the upper fiber here on this side. So concave down, concave up for this positive moment. So that's the elastic curve. So that's it for this video. I hope that you were able to follow and understand the explanations and the solutions. For more examples, you just visit my YouTube channel. There are many examples there, especially in the construction of shear and moment diagrams. Although some methods are different, like slope deflection equations and moment distribution method.